All right, so we're now in section 1.2 in Stewart, and we're going to start by talking about mathematical modeling. So our objective here is to understand the modeling process, as well as introducing some real-world context to what we call word problems. Now, I understand, both as having taken these classes before and now as an instructor, the word problems are where most of us have some hesitancy, anxiety about in math. That said, why we need to understand word problems and why I want to focus on getting comfortable with them is because they really are important. And hopefully this video underlies why that's true. So, what is the modeling process? So, we want to begin by thinking about this as flow. And we begin with the problem. And it's not necessarily a problem in a bad sense, but it's something that comes from a specific discipline. So if you are a student in this course, you are most likely going into a B-STEM major, so business, science, technology, engineering. And these are very common areas, disciplines, where we will be encountering these reference models. So the natural and social sciences are our focus here. And how do we identify what the problem involves? Well, when we identify what we're actually looking at, we're talking about quantities that are involved. All of this must be quantifiable. And this results in variables. We're interested in requirements or constraints. So what must be true about the phenomenon that we're observing? And what's our task? So what is the process that's involved, right? So what is the object or the process or the objective? And that's where we bring in the math. So the process of modeling takes the problem and then creates the model around it. And there's a couple of different ways of doing this, but we always want to focus on whether we have collected data, which we then fit our model to conform to these data. And we should observe expected outcomes. So in goes some explanatory variable, out comes some dependent variable or response variable. Of course, we want to check that our constraints are met. So that typically means we have to clarify something about the model, and our kernel, or what the heart of this thing is, typically is some function. And whether that's in one variable or multiple variables, that's up to how complicated this model may be. And lastly, we get some feedback. This feedback will allow us to improve and refine the modeling process. So we check the conclusions that we draw. We collect new data and test the model. And then we assess and adapt. So depending on what feedback we get, then we might need to re-strategize and change something in the model. So fundamentally, this takes us all the way back here. It is cyclical. Sometimes there's just no refinements to make, but oftentimes there is. All right, so let's see an example so that we can really understand what we're talking about here. And this is the motivating example that we started with in the beginning. So our problem is we want to model the electric field of a point charge, an electron, a proton, some other particle. So where does this come from? So we're talking about physics, but specifically we're talking about a branch of physics that we call electromagnetism. And we can get even more specific than that. We're talking about electrostatic fields. But so once we have this, let's identify what quantities are involved. So what quantities are involved include things like the field strength, what we call E. So how much field is experienced by something else in that vicinity. And that has newtons per coulomb units. We're talking about charge. In coulombs. And distance in meters. Typically scales much smaller than meters, but what are the constraints? Well, as charge gets very far away, E is negligible. We have to account for positive and negative charge because both exist. We're going to ignore external forces like gravity. And distance is always positive. And so based on the data that we collect, this is done using all sorts of experiments, which you would be best served by learning in your your Physics 420 class. But the model itself, so we find that electric field strength is proportional to, the symbol means proportional to, r raised to the negative 2 power, given charge Q. This is what we also call an inverse square law. And it's famous because this kind of relationship appears also in gravitational force. So they behave similarly. And we find that the actual function, so the actual function that governs this relationship is E as a function of R is equal to K times Q over R squared. Let's make that more clear. Where K is an experimentally defined constant of nature, which is approximately 9 times 10 to the 9th newtons times meters squared divided by coulomb squared. which is also known as Coulomb's constant. So there is everything that's showing up. So we have charge. So electric charge. Of course, it should depend on that because, if there's no charge, then there's no electric field. Here's the distance from the charge. And this is electric field strength. And so we see that we actually get two different cases where we're looking at, let's not do that. If we're looking at positive charge or negative charge, So for a positive charge, we're looking at something that looks like this. And for a negative charge, it looks like this. And what we conclude from this positive charges act like sources. Negative charges act like sinks. So in other words, if you have something like a proton, around that proton, something that is located some distance r from that proton, it's going to feel a positive force outward. So it's going to push it outward along these things called electric field lines. But for a negative charge, the same particle at the same distance, r, is going to feel a negative force pulling it toward the point charge, the electron. And this tracks experimentally with what we know about classical electrostatic fields. Of course, we're not going to get into any more detail than this, but if you can imagine this phenomenon right here, where we have a negative charge, behaves something like gravitational field. And for a proton, it's the opposite, which doesn't have a counterpart in the classical theory of, or in the general theory of relativity, I should say. So, lastly, what are the things that we use this for? So we've talked about how this is specific to not any discipline in particular, but can be applied to any discipline. And it's a cyclical process that depends on collection of data, observation, empiricism. But also in practice, obviously, depends on something like describing trends, or maybe you need to publish something, or grant money is involved. But the less we say on that, the better.